Welcome to lecture number 33 for ECE 461 Control Systems, Meeting Design Specs in the Z-Plane. Now we had a similar lecture in the S-Plane, where to meet the design specs in the S-Plane, I designed a compensator K of S by adding poles and zeros. If you want to make the system type 1, you add a pole at S equals 0. If you want to speed up a system, you start canceling stable poles, put them out of harm's way to the left, pull the root locus left, and then you add a gain k to specify where you are in the root locus. Same thing in the z-plane. In the z-plane, I'm going to add poles and zeros in k of z. The zeros will cancel slow, stable poles. For every zero that you add, you have to add a pole. That keeps the system causal. And if you have a type 0 system, add a pole at DC, which is s equals 0 or z equals 1 if you want to make it type 1. All the remaining poles go someplace out of harm's way, typically towards the origin. Because in the z-plane, the origin is infinitely fast versus the s-plane minus infinity is infinitely fast. A couple caveats though. There are a couple things to avoid in the z-plane. When I place my poles and zeros, do not ever cancel the unstable pole. Don't ever put a 0 outside the unit circle. I also don't want to put a pole outside the unit circle. The reason for that is testing. When you test your feedback system, typically what you do is you start with a very small feedback gain and start increasing the gain until you get the right overshoot. Part of the reason for that is sign errors happen. If I have a pole, say at 0.9, and I pick my feedback gain correctly, that pole at 0.9 will start shifting left, speeding up as I increase the gain. If I've got a sign error, that pole at 0.9 will start going the wrong direction. So typically what they do in the test labs is the person in charge of the lab will start with a gain that's almost 0 and start slowly cranking up the gain. If the system starts behaving worse and worse, they'll shut down the experiment, tell the control engineer to go check your numbers. If it's starting to behave better and better, then they might actually apply the gain that you had suggested. A reason for that, again, like I used to work at GE aircraft engines, and it costs $10,000 to run a test on a jet engine. It's $10,000 a minute, $10,000 an hour, something like that. It's $4 million if you blow the engine. So if you have a sign error and you took this pole at 0.9 and moved to 0.5, and instead with the sign error you took that pole at 0.9, moved it to 1.5, that's explosively unstable. You turn on the jet engine, it flies apart, you just lost $4 million. You don't want that to happen. So likewise, you start with a small gain and increase it to make sure that things are getting better and better. That only works if you're open loop stable. If you're open loop unstable, the gains have got to work as soon as you turn it on. That's part of the reason the B-2 bomber was so expensive. The B-2 bomber is open loop unstable. So when they built the aircraft and test flew it, they had to make darn sure there were no sign errors. And in fact, the test pilots in the B-2 aircraft said that the airplane flew almost exactly like the simulators, which says a lot. The modeling the aircraft is extremely accurate. The feedback gains were correct first time they plugged it in. But to do that, you wind up with a $2 billion airplane. In the commercial market, you really want systems which are open loop stable. Meaning, back at the ranch, when you design your controller, make sure the controller has poles that are stable. In addition, I don't want to put any poles on the negative real axis. What that does is, suppose my pole's at minus 0.5. My transients decay is z to the k, so this would be minus 0.5 to the k. I'd wind up with a negative, positive input. That chattering, it changes every sample. That chatter tends to break mechanical systems. So the constraints, when you place the poles of the compensator, keep them outside the unit circle and keep away from 180 degrees. Otherwise, it's just like the S-plane. Go through a design example. Suppose I took everyone's favorite system, the heat equation. I've got 3 poles, one at minus 3, minus 1, minus 3, minus 10. If I had this one, again, think heat equation, RC filter, Cessna, something that's open loop stable. Design a feedback control system so that there's no error for step input, 20% overshoot for step input, and a 2% settling time of 4 seconds. Now, the first method, I'll analyze this in the z-plane. First, you have to pick the sampling rate. I want a 4-second settling time. If I pick a 200 millisecond sampling rate, that gives me 20 samples in 4 seconds. And if you think about it, the microprocessor's got 20 iterations to figure out what the input needs to be to hold the output. 20 is a pretty reasonable number. If I had to do it by hand, I could probably do it in 20 seconds or 20 samples. A computer could probably do that as well. If I get around 3 or 4 samples, that's going to be really hard. If I go more than that, then, like the previous lecture, the sampling rate is faster than it needs to be, and that causes problems as well. Once I pick the sampling rate, convert g of s to the z-plane, and here I used z as e to the st, took the poles at -1, -3, -10, converted them to the z-plane as e to the minus st, 0.81, 0.54, 0.13. Next, translate the design requirements to root locus terms. I want no error per step input, meaning I want g times k to be type 1. This is currently type 0, so I need to add a pole at s equals 1, or at z equals 1, s equals 0. I also want to place the closed loop pole at -1 for 4-second settling time, -1 plus j2 for 20% overshoot. That's in the s-plane. Convert the z-plane as e to the st. I want to place the closed loop pole at 0.75 plus j.31. So come up with a compensator that does that. So the compensator I'm going to pick is, I'm going to add a pole at +1 that makes it type 1. I'm going to cancel a stable pole right here, 0.81. And I need a little bit of freedom. I need to put this point on the root locus. So let's add another 0 and a pole. The pole I'm going to slide around. What the pole does, that extra degree of freedom, I cancel the zeros until I'm too fast, take this pole and slide it around, and slide it so that the root locus passes through 0.75 plus j.31. I don't really have to draw the root locus here. I just need to make the angles add up at that point. So take everything that you know, this guy right here, analyzed at your design point, 0.75 plus j.31, find the angle, and it's not 180 degrees. I'm off by 48 degrees, meaning that the angle of z minus a must be minus 48 degrees. Doing some trigonometry, this side is 0.31, so this side is 0.31 over tangent of 48 degrees. And then a, this point right here, is going to be the real part, 0.75 minus 0.31 over tangent. So a is 0.46. Once I know a, I can find k. At any point in the root locus, g times k is -1. So here's g times k. I got rid of 2 poles, put one at the origin, the other one at 0.46. Analyze at your design point, and you get 0.8 at 180 degrees. The 180 degrees tells me that I'm on the root locus. That's good. The 0.8 says that k is wrong. Pick k to make the gain 1, so k is 1.24. And here's my compensator. The acid test is, does it work? Acid test is throw it in Simulink or VisSim. Here's the actual plant. Notice that's S-plane. Here's my compensator in the Z-plane. I set the sampling rate to 0.2 seconds. You see the little stair steps right here. And the overshoot that I get is a little bit off. Again, the reason I'm a little bit off is because my S to Z conversion, I needed 1.5 zeros at z equals 0 to get the delay right. I don't know how to do 1.5 zeros. So if I call that a single zero, round down, my model has too much delay. And so I overestimated the delay, I overestimated the overshoot. If I design for 2 zeros at z equals 0, I'll underestimate the delay. So the actual plant has more delay than I expected. I'll have too much overshoot. So either way you do it, you're either too high or too low. But you're close. That's one approach. Second approach is to use the mixed plane approach. This is actually the approach that I prefer. Notice that on the root locus plot, all I really care about is this one point. At that one point, I want g times k to be -1, or the phase to be 180 degrees. I don't care about the rest of the root locus plot. I only need that one point. So likewise, if I took this system, the zero order hold, k of z, and g of s, multiplied together, it does have a root locus. I don't know how to draw it because I have mixed planes, but I don't need to draw it. All I need is 1 point. So what we're going to do instead is analyze the hybrid system, the plant g of s, the sample and hold, half sample delay, and k of z. Pick k of z so this has a phase shift of 180 degrees at s equals minus 1 plus j2, and the z equivalent 0.75 plus j.31. The procedure to do that is I'm going to pick k of z. I know that I need to make it type 1, so add a pole at z equals plus 1. I want to get rid of the pole at minus 1, so cancel it. This is pole 0 cancellation. This is s-plane, that's z-plane. It doesn't really look like it, but if you relate, z is e to the st. Minus 1 s-plane is 0.81 z-plane. Cancel the pole at minus 3, and then add a pole. I've added 2 zeros, I've got to add 2 poles. This one is the one I slide around. Pick A so that the angles add up. And the angles add up mean that my plant times my zero order hold times k of z is equal to 180 degrees at my design point. So trying that, take this guy, plug in s equals 1 minus 1 plus j2. This first term is a complex number. E to the minus st is a complex number. Z is a complex number. So this is everything I know. I don't have that a term in there, z minus a. Add them all up, I get minus 127 degrees, meaning I'm off by 52.04 degrees. What that tells me, doing some trigonometry, here's my design point. I'm off by 52 degrees. So this point A, where my pole is, has to be, this side is 0.318 over tangent of 52 degrees. That's to the left, 0.75. So A is 0.5054. So I know the form of k of z. To find k, at any point on the root locus, g times k is minus 1. So take your g of s times zero order hold times k of z. Analyze that s equals minus 1 plus j2. And in the z-plane, that's just z is e to the st. Analyze the corresponding spot in the z-plane. And I get 180 degrees, saying, yep, I did that right. I got this pole so that the angles add up to 180. Gain's wrong. To fix the gain, add k. So k should be 1.2456, and there's k of z. The ask to test is, does it work? Take your k of z, your plant, set the sampling rate to 0.2 seconds, close the feedback loop and run, and sure enough, the overshoot's 20%. So either way works. I personally prefer the second way, partly because it gives you the right answer, and also because I don't have to do that S to Z conversion, which is really annoying. I just have to take g of s and the zero order hold and k of z, design in one shot. The trick behind it, it's not real obvious, but this is pole 0 cancellation. The pole at minus 1, minus 3 cancels with the zeros at 0.81 and 0.54 because these are z-plane, that's s-plane. There is a mapping, the mapping is c to the st, but it's not obvious that how this relates to that system g of s. But if you get familiar with the z and s-plane, get familiar with e to the st, I know that there's mapping from one to the other. This actually is pole 0 cancellation. So that's lecture number 33 for ECE 461 control systems, meeting design specs in the z-plane.